All right, guys, this is our last lesson in our acid base unit, and it's titled neutralization point. So we're going to be looking for the neutralization point. You guys remember, that should sound familiar to you. Remember, acids and bases neutralize each other, and we're going to use the process of what's called titration. All right. She says, did you know that for every dollar a man makes, a woman gets 70 cents? What? That's so unfair. I know, right? He's like, well, if I'm doing all the work, why are you getting money? He didn't quite understand what she was saying. So anyways, you guys, we've seen this video before.
I understand the differences between strong and weak acids, but why does the hydrogen ion combine with water? Let's look at the particle view of HCl and water again.
So you guys remember what we were saying is, what makes acids acids, right? They tend to donate hydrogen ions, but you guys remember, in actuality, the hydrogen ion by itself does not exist in an aqueous solution. It will attach to a water molecule. So this is showing that hydrogen chloride, HCl.
A hydrogen atom has one proton and one electron.
See how the hydrogen goes to the water molecule.
The hydrogen ion is simply a proton.
So even though we write H+, this is just a review, guys. In actuality, it exists like such.
A proton doesn't exist in an aqueous solution.
H3O+.
It attaches to one of the lone electron pairs on the oxygen atom.
Then the correct equation for the ionization of HCl would be hydrochloric acid plus water yields chloride ions and hydronium ions.
Yeah, see, that's showing the same thing as this. It's just more appropriately written as hydronium ions. Okay, so you guys, we're going to go back to our molarity equation. You guys remember our molarity equation was molarity is equal to moles over volume. So let's say we want to, and you guys remember molarity is a measure of concentration. So let's say we want to get moles by itself. To get moles by itself, we multiply both sides by volume, and then we end up with this. Concentration times volume is equal to moles, same thing, okay? So that's just a rearrangement of our molarity equation. So, right, and that's kind of how I wrote this. Molarity times volume is moles of molecules. But now, you guys, when we're talking about acids, we're going to look, not talk necessarily molarity so much as normality. And you guys, it's not my fault. I'm not just trying to make life difficult by introducing new terms. This is just a term you guys need to become familiar with. But if you'll notice, normality is just really the molarity of an acid. Think about, you guys, what is it that makes an acid an acid? When we think acids, you guys remember, aren't we thinking the hydronium ions? The H+ ions, same thing. So you'll notice, just like molarity, it's moles of the hydronium ions per liter of solution. Just like molarity was moles per, this is actually, molarity is actually moles over liters, but that's the same thing as a volume, right? And that's kind of what that's showing us. Okay. So, so basically, if we just change it, so then we would just kind of change this slightly to reflect normality. So then instead of molarity, we'd say the normality of an acid times the volume of an acid would give us the moles of the hydronium ions. Okay. All right. You guys, we can also do the you guys, just so you guys can see the difference. Here's really the difference. Let's say I had 1 molar hydrochloric acid. You notice I'm using red, and that's to remind you guys that that's just to remind you guys that you guys remember acids turn blue litmus red, acid red. So if it's 1 molar hydrochloric acid, that's 1 mole per liter of hydrochloric acid. You guys, that would be the same thing as 1 normal hydrochloric acid. And the reason is because for every hydrogen chloride molecule or hydrochloric acid molecule, it has 1 hydrogen. You guys remember, that's what the normality is. It's the moles of hydronium ions, hydrogen ions. Here's where there'll be a difference. Let's say we had 1 molar sulfuric acid. And you guys, look at the difference. In sulfuric acid has 2 hydrogen ions it could potentially donate. Right? Remember, hydrochloric acid only had 1. So what would be the normality? If the normality is defined as the potential moles of hydrogen ions per liter, well, if it's 1 molar, it would be 2 normal H2SO4. You guys see, you're just taking into account the fact that it has 2 potential hydrogen ions that it could donate. All right. So you'd see in this case the normality is twice the molarity, because for every 1 H2SO4, there's 2 hydrogen ions it can donate. So that's the slight difference, you guys, between normality and molarity. Hopefully you guys realize it's not terribly different. Okay, now if we're going to be talking about the normality of a base, I bet you guys could define for me how is the normality of a base defined? If the normality of an acid is defined as the potential moles of hydronium ions per liter, when we're talking about the normality of a base, you guys remember, what is it that makes a base a base? When we think of base, we think hydroxide ions. So the normality of a base would be the potential moles of hydroxide ions per liter. So for example, you guys, let's just do a typical base. We've got 1 molar NaOH. You know what? Here, I'm going to mix it up a little bit. Let's say it's 2 molar NaOH. The question is, what would be the normality? Well, what we do is, just like with when it came to the acid, we look at how many potential H plus ions can it donate. When it comes to the base, we look at how much potential hydroxide ions could it donate. And you can see there's 1 OH for every one of these. So if it's 2 molar, if it's 2 moles per liter of NaOH, then the normality, it's going to be 2 normal NaOH. It's going to be 2 normal. Okay, and you guys see it's the same because there's 1 OH for every NaOH. Let's say we have 2 molar magnesium hydroxide. No, you know what? I'm gonna change that. We'll use a strong base. A strong base would be strontium hydroxide. Okay, look at the difference here, guys, on this one. You guys remember, you're going to see the potential hydroxides. You guys look for every. And here's the reason why we say it like this, guys. Oh, and I'll show you guys this in a sec. Right, if you have strontium hydroxide, when you put it in water, what's going to happen is it's going to break up into its respective ions, strontium ions, but get this, guys, look, there's 2 hydroxide ions, so there's always 2 for every 1, and so that's going to be reflected in the normality. So if it's 2 molar strontium hydroxide, the question is, what would be the normality of this solution? And the normality, you guys will look, well, if it's 2 molar, if there's 2 for every 1, then it's going to be twice whatever the molarity is, and it would actually be 4 molar strontium hydroxide. So you guys see what we do is we just multiply the molarity by 2 because there's 2 hydroxides for every 1 strontium hydroxide. So hopefully you guys see the slight, change that we make when you're converting molarity toward normality. So you guys, in like fashion, if we set up the equation the same, we'd have the normality of the base times the volume of the base would give me the moles of hydroxide ions. Okay. So now, you guys remember in neutralization, the reason why acids and bases neutralize each other. You guys think about it. The hydronium ions. You guys, what do acids do? They donate hydrogen ions. So what would the hydronium ion do? It would donate a hydrogen ion to hydroxide. So now what does the hydroxide become if it has an H plus ion? It becomes a water molecule. And what did this become when it gave up a hydrogen ion? It became water, and this became water, and then we end up with 2 water molecules. See how the acid will neutralize the base by forming water. Okay? So look at an example. This is by the way is a stomach. Okay, so in the stomach, you guys know you have gastric juices that would be acids, and the acids in your stomach help break down food, right? Well, sometimes you can, especially if you eat acidic foods like tomatoes and stuff a lot, you can build up a lot of acid in your stomach, so much that you have acid indigestion.
The stomach secretes gastric.
So you guys can probably predict, that keeps going, you guys can probably predict, how are we going to solve this dilemma of the pain associated
The stomach
with
secretes
acid indigestion? What are we going to add? We would add
The stomach secretes gastric juices that contain strongly acidic hydronium ions, H3O+. The strong acid can be counteracted with the weak base in sodium bicarbonate, NaHCO3.
What happens, guys, with this
First,
base?
sodium and bicarbonate ions separate, and sodium becomes a spectator ion. The bicarbonate ion donates a hydroxide ion in reaction with the hydronium ion to produce 2 molecules of water and 1 of CO2.
You guys see the ultimate result was the acid in the stomach donated a hydrogen ion to the carbonate ion. To the bicarbonate ion, and so then remember that OH group that was originally attached now has a hydrogen, and so then it combined with the hydrogen forming water. And you guys see the ultimate result. Now look at how much hydronium we have in our stomach. We have we have 2 of the hydronium molecules, whereas before, you guys remember, we had 3. So what we've done is we've reduced the amount of acid by adding a base. The acid and base neutralize each other, but you can see it's still an acidic environment. Why? Because we had more acid than we had base. So the question I have, though, is when will there be complete neutralization? When will all of the acid combine with all the base to form water? Wouldn't you guys agree it will have a complete neutralization when you have the same amount of moles of hydronium ions as you do the moles of hydroxide ion, when those are equal? So now, like going back to our equation here, okay, so we have these 2 separate equations. So at the point of neutralization, what can we say? The moles of hydronium ions equals the moles of hydroxide ions. So if this equals this, you guys, what could we do with those 2 equations? Wouldn't you guys agree? If Na times Va equals this, and Nb times Bb equals this, and at the point of neutralization, this equals this, what can we say? Can't we say this equals that? And then we end up, so these are the same, and then we end up with this equation. Na times Va is equal to Nb times Vb. This is called the normality equation. This is the equation that you would use when working with a problem in which you are neutralizing an acid with a base or a base with an acid. So you guys write this down in your notes. It's very important. Na times Va is equal to Nb times Vb. That is our normality equation. Now, you guys, in the lab, we would use this equation in a process called titration. I'm going to do a very simple one here. But in the lab, if we wanted very precise measurements, we'd use a long cylindrical glassware called a burette. And so then you would have to measure a certain volume, and I'm going to do a simple titration here for you guys to see how we use this process and what kind of information we can get from this process. But anyways, I'm just showing you guys what a burette looks like. If we return to the classroom, we would use this glassware once again, and it has a little tip here, which allows you to add a little bit of solution at a time so you can make very precise measurements. And this is just showing when you are going to measure it, you don't want to have it outside of the range of graduated values. Otherwise, you wouldn't be able to accurately indicate what volume that is. So, for example, if you had to read the volume, and burettes are different, you guys will notice. Look at how the numbers go different. In a graduated cylinder, the numbers go up. This time it's going down, and that's because usually you would start with a higher volume, and then you would add a certain amount. You would open up the valve, and then the solution would come out the bottom, the tip, and then this would be the final volume. And so you guys remember how you would determine how much volume you added. You take the final volume minus the initial volume. And so the reason why it's like this, then I start with a value like this. You guys see how this, you would read this volume as 9.4. It's 9.4, and I would subtract whatever the initial volume, in this case, let's say it was 8.4, and you're gonna get a positive value. That's why the numbers are written different. But anyways, because I'm gonna move on from that. Let's go with this problem. You guys write this down. This is the problem. We're going to use the process of titration and the normality equation to answer this question. It says, find the molarity of HCl using 25 milliliters of 1 molar calcium hydroxide solution. Okay, so here's the scenario, guys. Let's say here I have my calcium hydroxide. You guys should recognize that as a base. You see the hydroxide ions. So let's say I have, let's go with this. Let's say I have some hydrochloric acid, okay? Let's say, and so when, let's say a lab tech made the hydrochloric acid, but then they didn't label it correctly, and let's say they put hydrochloric acid, I just put acid here, but let's say they have hydrochloric acid, but you guys can see, obviously, what is glaringly missing from this is the concentration. You guys remember, whenever you make a solution, not only do you identify what the solution is, but what concentration is. So if I were to find this acid in my stock room and a lab tech from previous years didn't label it, somebody might think, well, if I don't know the concentration, I can't safely use it. Am I going to have to dispose of it? You do not necessarily have to dispose of it. What you can use is the process of titration, and that will allow you to ultimately figure out what the concentration of this is. So that is the whole objective, guys. I have an acid, hydrochloric acid, and I want to find what is the concentration and molarity for this acid. And we can do that by what we call titrating with, with a base. So that's what I would do. So I have my acid, okay? And you guys remember, I can use my normality equation at the point of neutralization, because that's when this is equal to this, right? And you guys remember we just arrived on a few slides ago. So what you would do is, think about it, I got my acid here, my hydrochloric acid, I don't know the molarity. Here I have my base. And let's say I know my base, I know I have 25 milliliters of a 1 molar calcium hydroxide solution. So that's my base. So I could neutralize my base with my acid, right? So I would proceed to pour my acid into my base until I reach the point at which it's neutralized. But I think a lot of you guys are already realizing, what would we not be able to know at that point? Think about it. I could add my acid, and we say the point at which it's neutralized, that would be the point at which the amount of hydronium ions from my acid is equal to the amount of hydroxide ions from my base. But you guys would agree, if I take this clear liquid acid and then pour it into my clear base, you guys would agree, I wouldn't know at what point have I reached the neutralization point, or you could call it the equivalence point. Probably more appropriate to call it the equivalence point. So there's one additional thing we have to do. We have to add what's called an indicator. And in this case, I'm going to use bromothymol blue, okay? And you guys, an indicator, I think we talked about before, it's much like the litmus. You guys remember litmus changed colors depending on if it was in an acidic environment or a basic environment. So I'm going to use this bromothymol blue. I'm going to add it, okay, to my base. Okay, so I'm going to add it to my base. And you guys can see bromothymol blue, it's an indicator. When in the presence of a base, it is what color? And not surprisingly, it is blue. Okay, so this is my base. Okay, so now what I'm going to do is, so here, before we start our titration, let's just show you how we'd use the equation. You guys, just like with the dilution equation, we're going to list what we know. Okay. So I got Na, Va, Nb, Vb. Okay. So at this point, I know I have 25 milliliters of my base. That would be the volume of my base. I've got 25 milliliters. The question is, do I know the normality of my base? You guys check this out. I know the molarity. You guys remember normality is the moles of hydroxide ions per liter, whereas the molarity was moles of the whole calcium hydroxide per liter. So all you have to do is, you look, for every calcium hydroxide, how many hydroxide ions do I have? I have 2 for every 1. So I have twice as many hydroxides as I do my calcium hydroxide. So if the concentration of the calcium hydroxide was 1 molar, wouldn't the concentration for my hydroxide be twice that? It's going to be 2 normal. So that's the normality of my base. Okay, and you guys at this point, you guys remember, what am I trying to find? It says find the molarity of hydrochloric acid. I want to know the concentration. I don't know the concentration. That's what I'm looking for. And now we're going to use the process of titration to figure out the volume of the acid that was needed to neutralize that base. So check it out. So you guys, this is what we would have normally done with the burette, that long, skinny glassware that I showed you on previous slides. I'm just going to be a little, we're just going to do simplistic here. So look, I'm going to add some acid, okay? And then I would stir, okay? And the fact that you guys see it's blue, what does that tell you about this solution now? It's still basic, because remember, bromothymol blue, the indicator, is blue in the presence of a base. So what do I have to do? I got to continue to add my acid, okay? So I'm going to continue to add it. I'm going to stir it or swirl it, and you see it's still blue. So you guys, have I reached the neutralization point yet? No, I haven't. I got to continue to add acid. So what's dominating right here? In this solution here, I still have more hydroxide OH minus ions than I have H3O plus or H plus ions, right? So I got to continue to add some more acid, which adds more H plus, H3O plus ions. Okay, now I don't know if you guys noticed that color began to change a little bit, indicating I'm probably coming pretty close to the neutralization point, the equivalence point, the point at which the amount of H plus ions in my acid is equal to the amount of OH minus ions in my base. Okay, so I'm gonna go, and so And you guys can see the purpose for that cylindrical tube is so I can add just a little bit at a time. I'm being kind of crude here. Once again, it is still a base, but I don't know if you guys noticed the color was changing. And you guys, what you got to be careful is when you guys do a titration is you don't want to overshoot. I don't want to add, so now I have more H plus ions than I add OH minus ions. We want to get right at that point at which the H plus ions that were added is equal to the OH minus ions that were present. And I swirl it, and now check it out, guys. It's no longer blue. In fact, it's a little, I probably want to add just a little bit more. And what you guys will find is, now you guys know, in the presence of a acidic, so now all of a sudden what happened? We went from a basic environment, a basic solution, to an acidic solution. And you know what, in this case, I probably just slightly over poured because it's an acidic solution. And you can see bromothionyl blue, which is an indicator. In a base, it's blue. And you guys see in an acidic environment, it's yellow. So let's say this was that's the point at which I've reached neutralization. So now it's neutralized. So the question is, how much acid did I add to neutralize that base? Well, look, I started with 25 milliliters of hydroxide ions. Now, if I read what is the volume of my solution, it's 40 milliliters. So obviously, how much acid did I add? Well, I just go 40 minus 25. I added 15 milliliters. It took me 15 milliliters. And ideally, what I would have done is just seen how much acid I had originally, right? And that would have been what was in that burette, was how much acid I had originally, and then I would proceed to add it to the base, which is at the bottom of the burette, and then I would take the difference of however much acid I had and how much I have now, which would equal the amount of acid that I added to the base. And so that would equal 15 milliliters. So now, you guys, I have an equation in which I have one unknown, and I can solve for that unknown. Remember, it's Na-Va, here, so I'll just write it out again, is equal to Nb times Vb. So if I want to solve for Na, the concentration of my acid, I divide by Va, you guys see that to get it by itself, and that is my equation. So the normality of my acid is the normality of my base, which is 2 normal, times the volume of my base, which was 25 milliliters, divided by the volume of the acid, which was 15 milliliters. You guys look, milliliters cancels out. 2 times 15 is 50, divided by 15. I got to do that. And I get 3.33. So the normality of my acid is 3.33 normal. But you guys see what I really wanted, because we don't typically put normality when we indicate the concentration of a solution. We do molarity. But you guys think about it. Remember, my acid is HCl. Remember, and I just look, I'm looking, oh, for every 1 HCl, there's 1 hydrogen ion. So the normality is going to be the exact same thing as the molarity. So it's 3.33 molar. That would be the molarity of my acid. So you guys see what titration is. Titration is the method by which we use an acid or a base of known concentration to neutralize an acid or base of unknown concentration in order to figure out the unknown concentration of that acid or base. All right, guys, that's titration. That is the normality equation, and that is it for today. Until next time.